Welcome to Rob 201, Lecture 2. So this week we get 2 lectures. Next week, because Monday is MLK Day, we only meet once on Wednesday. So quick summaries. We looked at why we do proofs. It's partly to have an understanding of how things work. And it's partly because that's how you build the foundations of mathematics, to make sure you're not building on a shaky foundation. One of the main methods of proof that we will use is proof by induction. And so you have something that depends on a quantity n. We just call it P for, I don't know, proposition n. And so here you can have the sum of the first n integers squared. And from playing around with the first 3 or 4 values of n, you form a hypothesis of what the right-hand side should equal, and then you set about trying to prove left-hand side equals right-hand side. And that's a very powerful way. So if you can show the base case is true, which in this case is easy, 1 equals a third plus a half plus a sixth, yes. And then the harder manipulation is showing if it's true at step k, it's also true at step k plus 1. Then you have established that it's true for all n equals 600 billion, even though you didn't work that high up. Archimedes' approximation principle was developed 2,200 years ago to compute pi, but it's a very general principle that we can apply to a lot of different situations. And so what we were doing at the end of lecture last time is just taking a monotonically increasing function. We did the algebraic calculations when that function was f of x equals x. And the key thing with Archimedes is we need a lower bound and an upper bound as a function of n. And then we want to show as the upper bound and lower bounds come together, they actually meet and they squeeze us in with the value that we are trying to compute. So when the line was f of x equals x, it was no big deal because we know the area of a triangle is base times height times a half. But for more complicated functions, we don't know that ahead of time. We don't have these nice closed form solutions. And so what we do is we form a lower bound on the area underneath the function. So the area would be all of this stuff. Okay, and the lower bound is we just go across, that's one rectangle, and the upper bound is here. So it's clear that the true area is between those 2 rectangles. And then we work out what we get as we sum up n rectangles for n an arbitrary number. And we form bounds something like this. Area n low less than or equal to what we're hypothesizing is the true area is less than or equal to the sum of the bigger rectangles to the area n upper bound. And if those 2 things go together for large n, then we can define the true area. And when we did that for y equals x, we were hopefully reassured when we obtained formulas, thank you Malwarebytes, we obtained formulas that seemed reassuring to us, because if the length is b, the height is also b, so that's b squared over 2, and the lower area is 1 times 1 minus n, and the upper area was b squared over 2 times 1 plus 1 over n, and we know what 1 over n does when n gets large, it goes to 0. So we do have the true area, and Archimedes' approximation principle works. Okay, so in this case, it's super easy to analyze what happens for large n. We have just really simple formulas. What we want to do, though, is use this as motivation for studying limits at infinity. So I'm going to ask you to draw this graph in your notes. I'll give you time to do that. And today we're looking at limits at infinity. And I'll define all these terms, L and epsilon, et cetera, in just a little bit. How are we doing on the figure? You're getting there? Yeah, I see you're still doing well. Max, is yours looking as fine as mine? Beautiful. Maya, how are you doing? Good. So we're going to do these limits in two ways. We will start with the hard way, and then we'll transition to all of the intuition we build up with our careful analysis to finding the engineering way, okay? So we will definitely transition to that. Okay, so the intuition of a limit is that the function should approach a given value if we go far enough out in the x direction. Okay, it should. So we're looking at the asymptotic long-term behavior of the function. The first initial wiggles we think of as it's transient, and then it's moving into a steady state. So that's the intuitive notion of a limit. And then L is our candidate value for the limit. And epsilon greater than 0 is our degree of precision. So who knows, maybe we can only force the function to get within 0.7 of L, and then it really wouldn't be a limit, as we'll see. But so epsilon is our degree of precision, our tolerance for how much the function can deviate from the constant L if we let x be sufficiently large. And then we're going to introduce n as a knob for tuning x greater than or equal to n to achieve the level of precision epsilon greater than 0. Now, what we'll see is that as we vary the level of precision, if we were to bring these two dotted lines in closer and closer, we will need to change the value of n in order to achieve that level of precision. So here, with the way I have epsilon drawn, we could literally take n here, and I'm going to call it n sub epsilon. But if I were to move whoops, moving the function, haha. Good, don't do that. Can I just, oh, I see, it's all grouped. If I were to move the level of precision, and you should do it symmetrically, then I'd have to move n. Okay? So I'm going to erase these changes and stuff, but I'm just trying to illustrate that the more precise we try to make the estimation of the function getting close and staying close to our candidate limit, we do, in general, have to change the estimate n. I'll put that one back. Is that clear? Okay, so n is epsilon is the level of precision. And so we see that in general. N varies with epsilon. And we denote this by either n of epsilon or n sub epsilon. So it's just a value that when x is greater than this, we want the difference of the function minus the limit to be within epsilon. And once again, epsilon is our tuning for precision. N is how far we have to push x out in order to achieve that level of precision. And that's what this figure is trying to capture. Okay, so that's the intuitive part. Let me just kind of write it down as a definition, and then we'll check it on a few examples. As practicing engineers, you will never do an epsilon definition of limits. You'll do the easy way that we will talk about later. But the easy way is going to make a lot more sense if we just go through the careful mathematics first. So this is the definition of a finite limit at infinity, meaning x becomes arbitrarily large. So suppose f takes 0 infinity to r is a function, and L, an element of the reals, is I'm going to emphasize finite real number, but all real numbers are finite. Okay, because remember, infinity is not a number, so infinity is not an element of the reals, and you can have really big real numbers, but all of them are finite. None of them are infinitely large. Then we say, limit as x goes to infinity of f of x equals L if for all levels of precision, so epsilon greater than 0, and since it's for all epsilon, this is redundant no matter how small, but it just helps to emphasize what we're focusing on. So no matter how precise you set the level of precision, there exists an n sub epsilon finite such that x greater than or equal to that value implies the absolute value of the function minus the candidate limit is upper bounded by our given level of precision. Okay. Okay, so going back to our picture. Here we could choose n epsilon, and if somebody else came along and they chose their n epsilon here, would that still be okay? And to answer that, let's just notice that if you find a bound for this that is true, and you replace it by 10 times that, then it's still true. So you don't have to find the tightest possible n, though in our examples, we will do that because to do something else seems kind of wasteful. But really, to check the definition, you just need to say for arbitrarily tight level of precision, I can find a finite bound such that there is no x bigger than that bound where this level of precision fails. So that's the idea. Questions? Anything online? No? Okay. So let's do some examples. So A, we'll start super easy. For x equals, for f of x equals 1 over x, and we're doing limit as x gets very large, we would guess that the limit is equal to pi? No. Quarter? No. 0, okay? L equals 0. So we make a hypothesis, and then let's suppose I give you a level of precision, and we'll just make it concrete instead of an abstract number. What is the value for n sub epsilon? Okay, so to do that, we're after this bound. Okay, so that's the definition. And for us, this is equal to 1 over x minus 0, and that equals to the absolute value of 1 over x. We want that to be less than or equal to 1/10 for x greater than or equal to n 1/10. Okay, so what value should we choose for n? Well, because we weren't trained in mathematics yesterday, we see that we need clearly, we need n 1/10 is equal to 10. So if x is bigger than or equal to 10, then 1 over x is less than 1/10. Now, if you had said n 1/10 equals 100, it's still true, is my point, okay? It's still true, it's just not tight. But nothing in the definition requires you to give a tight bound. So if you're doing a homework problem and you're within a factor of 4 of what we compute, we'll be happy, okay? If you just say, well, X bigger than a Google, which is 10 to the power 100, you're almost certainly going to be true, but you will not have shown us that you understand how to compute a bound, okay? So that's all. But in theory, it's still totally, totally true. And then for general, epsilon greater than 0, absolute value of 1 over x is less than epsilon for x greater than or equal to 1 over epsilon. And hence, n sub epsilon you can take to be equal to 1 over epsilon. So it depends on epsilon. And this one's tight. Did we have to compute it tight? No, I could have put 11 over epsilon and it's still fine. Okay, so those type of bounds are really straightforward, and we're going to move in just a little bit to problems that are not so straightforward. Let's just do one more straightforward problem. Let's take f of x equals 1 over x squared this time. Once again, as x becomes large, we understand that the limit is still 0. And then I'm going to specify epsilon as a quarter, just to start with. Okay, and so we write down what we want to check. That's usually the best step. The function is 1 over x squared. L is 0. And since x squared is always positive no matter what, as long as x is not equal to 0, we can remove the absolute value signs. Then we seek our n sub epsilon, n sub 1/4, such that x bigger than or equal to whatever this number is implies 1 over x squared is less than or equal to a quarter. And so again, this one is pretty straightforward because we know how to, if we invert positive quantities, it flips the inequality to greater than or equal to from less than or equal to, so x squared greater than or equal to 4. And since we're going x to infinity, there's no sense looking at negative x's, so we'll take x greater than or equal to 2. And then that implies we can take n 1/4 equals 2. Okay, so you write down the definition of what you're trying to check. You do the algebra, and because there's absolute value signs in there, it's easy to make mistakes with the inequalities, but you do your darndest to check that out, and then you find bounds. And then for general n, or epsilon greater than 0, we want 1 over x squared less than or equal to epsilon, and that's the same thing as x squared greater than or equal to 1 over epsilon. So we invert each side of the equation to do the algebra. Since everything is positive, inversion flips the sign of the inequality. And then that implies we need x greater than or equal to the square root of 1 over epsilon. Or if you want to write that as 1 over the square root of epsilon, it's the same thing. And so we conclude that n epsilon equals 1 over square root of epsilon. Okay, so for these, the derivation of the bound is, I guess I wouldn't call it tedious, it's straightforward. I would call it somewhat boring, okay? So let's do one more example and make it a little bit less boring. Okay, and then what do you think we need to choose L as? Okay, if you're going to evaluate a limit and you apply the definition, we need to come up with a candidate value for L. Anybody want to offer a half? Yep. And so what's the thought process? For x large, 1 plus 2x and 2x are the same thing for x sufficiently large. And then x over 2x, the x's cancel and you have a half. So that's the intuition. Okay. So we don't know that L equals a half works yet, but we suspect it does. So then we form our f of x minus L. F of x is x over 1 plus 2x. L is a half. Okay, so here we've applied the definition. The rest is just algebra. So it's not exciting. We're going to put these things over a common denominator. Surprise, surprise. That's how you often handle fractions, right? Put them over a common denominator. So the common denominator is the product of the first denominator and the second. And then we're going to have 2x and then minus 1 times 1 plus 2x. Okay, so that's putting everything over a common denominator. Then we do the algebra. We see we've got a plus 2x and we've got a minus 2x. And so this leaves us with minus 1 over 2 times 1 plus 2x. And then if we assume x is positive, so the denominator is positive, when we take the absolute value, all it does is erase the minus sign. So as we're looking at x going to infinity, we don't really care what it does for negative values. Okay. So now what is n sub epsilon? Okay, so we want to find the value. What does it mean? We want 1 over 2 times 1 plus 2x to be less than or equal to our level of precision. We're interested in x as a function of epsilon, so let's flip both sides, and we get 2 times 1 plus 2x less than or equal to 1 over epsilon. And then, okay, we'll divide by the 2. We get 1 plus 2x. Whoops, I didn't flip my, even though I said we should be doing that. 1 over 2 epsilon. Subtract 1 from both sides. And we get x has to be larger than 1/4 epsilon minus a half for this inequality to hold. And so that gives us n epsilon is 1 over 4 epsilon minus a half. Whew. Okay, so here's the key point, though, is that we can do and I'll call it like it is, the grungy algebra for toy problems and very little else. So the definition is wonderful. It tells us really what we're after. We're after a level of precision and then an estimate on how far we have to push x out to achieve that level of precision. But let's just go back to this problem. And imagine I had a cubic in the numerator and a quartic in the denominator, and now I wanted to go and start deriving all of these bounds, okay? How many of you know closed form solutions for cubics and quartics? Yeah, okay, that's the problem. You can do it numerically. Now, there are closed form solutions for the cubic, and there are closed form solutions for the roots of quartics, but for quintics and sixth power and beyond, there are no such solutions, so you could only do it numerically. Okay, so the insistence on applying the definition and giving the level of precision and calculating in closed form this bound, that's not going to work for real problems. Okay, so we need another way, and we're going to move towards that in just a little bit. Okay. Questions though on what we're doing? The concept, level of precision, how to do it for toy problems, but, you know, instead of 1 plus 2x, if that was 1 plus sine of x, and then there's an e to the x there, and you've got this transcendental equation you've got to solve, forget it, okay? It's not going to happen. So, you see that, I see that, I just want you to know that it's part of the lecture that we're going to build towards better methodologies here shortly. Okay, so now, before I write down this definition, let me do another graph, and this one I'll do live. I don't know. Let's take a function that's roughly x with sine riding on top of it and wiggling around. Okay. So does such a function have a finite limit? If it, just imagine it continues like that. And the answer is no, it does not have a finite limit. But we can formally define what it means that its limit as x gets large is infinite by you specifying some finite bound, and if you can give a bound on x such that if x is to the right of nk, the function is bigger than k, and you can do that for all possible values of k, then the limit of the function has to be unbounded or infinite. Okay? So definition, and this is well, I'll do it like this. Definition. The limit as x goes to infinity of f of x is equal to infinity if for all k positive, no matter how large, there exists nk finite such that this time when x is bigger than this bound we've computed, it implies that the function is larger than or equal to k. So the height. Okay, so we could go through and do similar calculations as the ones we just did for finite limits, but we're not going to do that. Instead, for our examples, what we're going to study are things that work and things that don't work. So if I have x of x equals x cubed, then we know what the graph looks like. It's just monotonically increasing, and we get limit x goes to infinity of f of x is unbounded. No problems there. Let me do something a little bit different. So what if I take x times sine of x? And I'll draw this one just a little, whoops. I'll draw this one a little bit more carefully than the previous one. Okay, so the amplitude is growing. If I were smart, I'd give myself okay. So, does a function like this converge to something that has a finite limit? Well, pick any number. Can you give a bound on x such that if x is to the right of your bound, then the function always stays within your level of precision of that number? And the answer is no, it just keeps oscillating. And then, is the function heading to infinity? And the answer is no, because for the limit to be infinite, we need that if you give me a bound, I can set a value of x that the function never drops below that. Okay? Whereas here, look what happens. Whatever value of x that we draw, okay, so if we set k there, the function is going up and coming down, going up and coming down. It doesn't get up above it and stay there. So this function has no limit as x tends to infinity, so as x gets large. Okay, so it's not just that the function takes on arbitrarily large values, because this function does take on arbitrarily large values. The limit is infinity. When you give me any finite bound, I can make the function stay above that bound. Okay, so that's the crucial notion for limits at infinity. You get above the bound and you stay there. Questions on that concept? Working for Max, that's good. Maya's getting her homework in EECS 215 done. No? Something else? Rob 311? Questions? No? You're good? Okay, so not just because the function's values get big, that doesn't imply that the limit is infinity. It has to get large and stay large, where this gets large, then it gets small, and then it gets negative, and it gets large again, etc. Okay, so has no limit. Let me do another example. And I'll attempt to draw a sinusoid. Okay, so this is sine of x. Can you tell? Good enough, right? So, it's clearly not heading off to infinity, doesn't take large values, but does it have a limit does f of x tend to a value as x gets large? And the answer is, well, the value can't be bigger than 1, okay, because it never reaches it, and it can't be less than -1, but even if I draw a value, say in here, it doesn't get close to it and stay close to it. That's the key idea. Okay, so limits, you need to get close to it and stay close to it as x gets large. So this sine of x, the limit as x goes to infinity of sine of x is undefined. It does not exist. So same as okay, and how do we reach that conclusion once again? It's because we know what it means to have a finite limit. You get close to a value, and then you stay close to it as x gets bigger and bigger. You don't deviate more than our given level of precision, epsilon, or the function has a limit that is unbounded and is infinity if no matter what level we draw, the function gets above it and stays above it. So there's a second. So here's a K2, and this would be NK2. And sine does not satisfy any of those definitions, so its limit is undefined. Cool? Okay. Questions? You love epsilons? Not so much, huh? Okay. Well, you're going to love this. Okay, let's do it now the easy way. And this is the way that all real engineers do it, and most mathematicians, this is part of their qualitative analysis as well. Okay, I'm going to start by looking at ratios of polynomials. So I'm going to assume the leading coefficients of my two polynomials are not equal to 0. Okay, so I'm going to write down b to the m, x to the m, b subscript m minus 1 to power m minus 1, plus dot, 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 all the way down to the constant term. Then a to the n, x to the n, a n minus 1, x to the n minus 1, dot, 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 a 0. Okay. Equals. Now I'm going to do something hopefully you think is clever. I'm going to factor out the highest term in the numerator and the highest term in the denominator, and then leave myself with b to the m, b to the m minus 1, 1 over x, plus dot, 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 b0 over x to the m, and similarly down here. Okay, so we've factored this into a product of two terms. Huh. Now, why is that useful? What happens to 1 over x when it gets large? Goes to 0. What happens to the 1 over x squared when it gets large? 0. And 1 over x to the m when x gets large also goes to 0. Okay, so the numerator on the right-hand side reduces to the constant bm. Let's look at the denominator when x is large. So when x is large, when x is large, we got this constant, that goes to 0, so this vanishes, the next term goes to 0, that vanishes, and all of this stuff vanishes. Oh, come on, I want my... So here, just on this part, the limit as x goes to infinity is bm over an. Okay, so we took this horribly complicated rational function where if we were trying to calculate the, given an epsilon, find the n epsilon, good luck, okay? It's really good luck. So that right term on the right is easy to handle. And then what about this term x to the m over x to the n? Well, if m and n are equal, what's the limit as x gets large? It's 1, because they cancel. And if m is bigger than n, what happens as x gets large? Goes to infinity. And if n is bigger than m, what happens when x gets large? It goes to 0. So we know exactly what happens to this complicated function. We can calculate the limit, and we're going to write it down in a second. But, you know, look at the simple function that we were dealing with here, and look at all of the algebra it took to try to find those bounds, okay? So it's just not practical. And if you're trying to do those bounds here, really, really painful. Okay, so but we understand what's going now because we did the epsilon delta, epsilon n bounds for 1 over x squared. So we've got the intuition. Hence the limit as x goes to infinity of b to the m, x to the m, plus b0 over a to the n, x to the n, plus a0. Got a few cases. 0 if m is strictly less than n, so the numerator is smaller than the denominator, we end up with something positive in the denominator after we cancel terms, and then that goes to 0. You get bm over an when the two terms have equal degree, m equals n, and we just get bm over an. Now what happens when m is larger than n? Well, if the constant bm over an is positive, then we get plus infinity. And if bm over an is negative, we get negative infinity. Okay, so one way to write that is you get the sign of this number.
I'm so sorry.
Yes, it's okay.
Got left behind.
What are you looking? What do you need? Just pen?
Daniel said he forgot his headphones.
I didn't see any headphones, but let's take a quick look. And I don't see any headphones in there either, sorry.
Okay.
Yeah, no.
So sorry for interrupting your class.
Hey, you know, all of us would want to be finding our headphones if we lost them. It's okay. So sine of b of m times infinity, okay? And this is for m greater than n. And the sign just means it's plus when bm over an is positive, and it's negative when bm over an is negative, okay? So now let's work some examples. fa of x equals, let's say, 20x squared plus 11x plus 14 over 1 plus 4x squared. And if x goes to infinity, I'm going to ask you guys to compute that. We'll do them all together. Let's write down the things, and if you guys are writing down the answers as quickly as I can write down the problems, then you'll be all set to discuss, but I'll give you a little bit of time. Minus 4x cubed plus 11x again. I'm just changing the highest terms here. And we'll keep the 1 plus 4x squared. Whoops. Compute the limits this way. And then fc of x equals, what do I got here? Minus 4x to the fourth plus 11x, who knows, square root of 2 over 2x squared plus 1. That's enough. Okay, so can we calculate these basically in our head with just a little bit of work here? So what is an in the first function? It's 20. And what is bm in the second one? It's 4. So we have 20 over 4. And the n is 2 and the m is 2, so they're equal. So this limit goes to, drum roll please, brrr, bingo, what is it? Yeah, 20 over 4 equals 5. Yep, okay. Whew. Second one. Leading coefficient in the numerator is minus 4, and in the denominator, even though I've written them backwards from how we usually do polynomials, just because you got to look for the leading the highest order term, it's 2. The numerator in the first one is cubic and the denominator is quadratic. So what happens as x gets large, this limit goes to, how about this side of the room? What do you think? So we've got minus 4 over 4 is negative, so the sign is negative. The numerator is 3, denominator is 2, x cubed divided by x squared is x, so it goes to minus infinity, yep. And then let me change this last one on you guys, just so we have a different answer. I'm gonna make this 6. Okay, so we've got minus 4 and 2, but do we care? Is the question. And the answer is no, because the highest degree in the numerator is 4, and the denominator it's 6, so the denominator wins and it drives this to 0. Okay, so that's how you do limits the easy way. Okay, let's take a short break. It's 5:30. Start back up, I don't know, 5:35, something like that. There we go, went to sleep. Moral of the story, never go around talking to students and trying to actually create any camaraderie or ambiance in the class, okay? Anything like that will always come back to bite me. Okay, so now that you can see what I'm doing, how does the story change for something like limit as a counting number goes to infinity and you had something like this? So before we had x, a real number. Now we're looking at a counting number getting large. What's your guess? Big change, no change? Okay. I know, nobody wants to take a chance of being wrong, okay? So I get it. I didn't want to be wrong in class when I was an undergrad either, okay? Totally get it. And the thing is, it's no substantial difference, okay? So how would you work this problem? Well, you would simply do limit n goes to infinity. We would factor out the leading term. And then this would leave us 1 plus 6 times 1 over n, and then 4 plus 11 over n squared. 1 over 4 is positive, and the denominator is winning, and so this would be, I'll just emphasize, plus infinity. Okay, so you can see, find lots of examples in the textbook like this. Examples 2.35 and 2.36 in the textbook. Okay, so nothing really changes. The symbols change, the domain changes a little bit. Okay. Now let's do a little bit more complicated example. N goes to infinity. And this is x plus 1 over capital N squared minus x squared divided by 1 over n. And it's not a ratio of polynomials, okay? So it's not a rational function. We just developed all this beautiful theory when we had a polynomial over a polynomial. Remember, x is not the variable that's getting large. It's just a parameter in here. N, capital N, is what's getting large. How do you do it? You first simplify this via algebra. And once again, the burden of calculus almost always comes down to algebra. Okay, so if we square x plus 1 over n, we get x squared plus 2 over nx plus 1 over n squared. Then we have minus x squared. I copy down again the 1 over n. And then I'm going to multiply by n. And the only reason I'm doing that is because I want to get rid of the 1 over n in the denominator. You could just multiply, so we multiply by n over n. Okay? So when you're confronted with something like that, simplify, turn it into a ratio of polynomials, and then you can evaluate your limits. Okay, so this x squared and this one cancel, and then we can see how the n's cancel for us, and we end up with, let's see, the n and the n, we end up with here 2x plus 1 over n, and this is over 1, and so that equals 2x plus 1 over n. And when n goes to infinity, the 1 over n goes to 0, and so the answer is 2x. Make sense? Okay, so you just expand out, and then you can apply the results. And so I'm going to write it down like this. Limit n goes to infinity, x plus 1 over n squared minus x squared equals 2x. So for those of you who have had Math 115, what did we just do? We computed the derivative of x squared using the definition of the derivative, which we will get to in chapter 5. That's all we did, okay? But maybe I hit it on you because I didn't call it delta or h for the perturbation. I called it 1 over n, okay? So I disguised the limits. Okay, so what I'm going to ask you to do now is to just put your pens down, and you can get this from the notes. I didn't know how much we would do. And I want to go through some material that'll help us understand how broadly applicable the stuff we're doing is with limits, okay? And I don't know if they cover this in a standard calculus course. They didn't cover it in mine when I was an undergrad, but you know. So, first thing, real numbers. So I'm just going to take x that's in the interval 0, 1 and do a decimal expansion of it. So D1 is the first digit, D2 is the second digit, D3 is the fourth digit, etc. And the digits are chosen from the numbers 0 through 9. Okay? And so when I write down x equals ... it's really a limit. So it's the limit as capital N goes to infinity, because we understand placeholder, places, and so the first digit is multiplied by 10 to the minus 1, the second digit times 10 to the minus 2, etc. And so this is covered in Math 350 and Math 450. So let me just ask you this. If I take 0.99999 ... So it's really a limit. What do you think it is? Oh, 1. Okay. Well, why is that? Well, 1 minus 0.9 is 0.1. 1 minus 0.99 is 0.01. 1 minus 0.999 is 0.001, etc. Okay? So you go 1 minus 0.99999, you've got 0 on the other side. So this is just applying the definition of a limit, right? It's purely the definition of a limit. So just like we were saying, our level of precision, you give me an arbitrary level of precision, I just use it to see how many digits I have to go out on 9 to arbitrarily well approximate the number 1. Okay. So you were probably taught in, I don't know, 6th grade that if you had repeating 9s that you had to round up, okay? And you had other things that were similar to that. Okay, so limits, the fact that when you're dealing with real numbers, you're really dealing with limits of rational numbers. For every n finite, the 0 point, d1, d2, d3, d4, ... stop at dn, that's just a rational number. And all of the numbers, the irrational ones, are then obtained from taking limits as n goes to infinity. So that's how you build the real numbers from scratch. And this is done, and once again, in Math 350 and 450. I alluded to this Wednesday of last week. So let's look at powers, x to power y. So we're all really good at x squared, x cubed. We're not too bad at roots, x to the 1/4 and stuff like that. And we can probably, most of us do, understand what it means if y is a rational number. So if I take x and I raise it to a rational number, so rational number I write over an integer divided by a counting number. The integers are -2, -1, 0, 1, 2, dot, dot in both direction, and the counting numbers 1, 2, 3, 4, etc. And if you want to throw in 0 in the counting numbers, that's fine with me. And so x to the p over q is simply the qth root of x to power p, but it's the same thing as taking the qth root of x and then raising that to power p. Okay, so it doesn't matter which way you do it. That's proven in chapter 1. But what does it really mean when y is an arbitrary real number? And so what you do is you take your arbitrary real number, you approximate it with a rational number, because we just basically, by definition, everything that has a decimal expansion, you truncate it, it's a rational number, and you can get finer and finer levels of precision by taking capital N bigger. And so you tell me the level of precision you want in the approximation of your real number by a rational, and then I can calculate x to power y as the limit, as say here, I'm using I as the index, and my level of precision, epsilon, is 10 to the minus I. So it gets very precise very fast with powers of 10. And I can just calculate the limit of this set, sequence, or index set of real numbers, okay? So it's no longer, once again, x is fixed, and it's the qi and pi that vary, but they're varying in such a way that they approximate y better and better and better. So that's really the definition of x to power y. And to see it in practice, just take pi, and we have its infinitely famous decimal approximation, and 3.1, the level of accuracy is better than 0.1, and 3.14, the level of accuracy is better than 10 to the minus 2, 10 to the minus 3, etc. And so 3 to power pi, for example, would be the limit as I goes to infinity of 3 to the ri, where these are the decimal approximations of pi. So it's just a definition, is what it means. And if you want to see this, you just go in Julia and write yourself a script and just kind of compute it, and you'll see you get the same thing. So, questions about how powers are defined for real numbers? I mean, because it's kind of abstract. What's the pith root of something, or the pith power, okay? I don't know. Well, now you know, okay? You approximate pi by rationals and you get better and better. Okay, so let's look at the inverse functions of powers. And so this is, here what I'm emphasizing is how you write down definitions. So what does it mean that a real number z is the yth root of a real number x? Well, its definition is that if you have z and you raise it to the power of y, you get x. That's the definition. That's what roots mean. And since we've defined powers for arbitrary real numbers, we now know how to do roots for arbitrary real numbers. So this is how you build a set of valid operations. And here I'm limiting to x non-negative because I don't want to deal with complex numbers. So we know the square root of -1 is the unit I, etc. Okay, so we're limiting the domain of our inverse functions when y is an arbitrary real number to x non-negative, greater than or equal to 0. So that's roots. And you define them by z is the yth root of x. When z raised to power y, you get x back. Exponentials. They're like powers, but in exponentials, we let the a be fixed, and we call that a base, and it's the top one that varies. Okay, when we're doing powers, the power is fixed, or the root is fixed, and then we're varying the lower one, okay? So this is fixed, and we vary x. That's powers, x raised to power pi, e, etc. Exponentials, it's the opposite. This is fixed, it's called a base, and then we're raising it to power x. So they're like powers, and you get the definitions of exponentials from the property of powers, but you just have to flip where the variable is going. And since we've been trained since we were like 4 years old to think of x as the variable, I've carefully put x in there, okay? But I could put x to power a and call x the base and a the thing, and it would be valid, but it wouldn't work very well. Just like if I have the equation ax equals b, I could change a and b and call x a and let b be equal to x. It's still a valid equation, but the symbols are such that you couldn't read it because you're used to ax equals b. Okay, so it's the same thing with exponentials. I've got my variable in the top. Okay, so if the base is bigger than 1, it's monotonically increasing. If the base is between 0 and 1, then it's the function, the exponential, is monotonically decreasing as a function of x. And if the base is equal to 1, well, 1 to any power is just 1. And so it stays 1. And so exponentials are invertible. Okay, so it passes, it's a function because it passes, let's see, it's invertible because it passes the horizontal line test, the vertical line test, whatever, whichever one it is. Okay, so it's monotonically increasing, and for a bigger than 1 and monotonically decreasing. When we put a negative exponent, it's by definition equal to 1 over a to the x, where the exponent is positive. And that's the same thing as a to the minus 1 raised to power x. Okay, so that's useful things to know. So these are things you guys seen, you use, etc. Logarithms, they're just like roots because they are the inverse functions to exponentials. So if I have a positive x, then y is the logarithm base a of x if and only if a raised to power y gets my x back. So that's how logarithms are defined. Now, I know in high school, logarithms terrorize students. You guys are mostly more experienced engineering students at Michigan, so you're no longer terrorized by logarithms, which is good. We will just compute them, okay? We're not going to be computing them by hand or anything. We use Julia, your calculator, go on the web and Google it, whatever. Now, because logarithms are inverse functions, the base can never be 1, because that exponential, 1 to x, is not invertible. Every x gives you 1, and there's no x that gives you any answer but 1. So when you're doing logarithms, the base should be positive and not equal to 1. And the reason for that is you cannot invert a to the y otherwise. Now, the 3 key properties of logarithms that we'll use throughout the term is that the log of a product is the sum of the logs. The log of a power is the power comes down and multiplies the log. Okay? And then that can be generalized that if you take any function into the reals and you look at x to power f of x, so that looks super complicated and really difficult to play with, But that function becomes much simpler when you use a logarithm. So the log of x to power f of x is just f of x times the log of x. So that's much simpler when we need to start doing derivatives, integrals, etc. The natural exponential and logarithm. So a not equal to 1, all of those things defined exponentials and logarithms. The natural exponential is when the base is taken as Euler's number. So I invite you to scan chapter 1.3.3 and follow Bernoulli's discovery of Euler's number by looking at compound interest, as I mentioned Wednesday of last week. And so it is also defined as a limit, and it's roughly 2.718 is Euler's number. What makes this exponential and logarithm more natural than using base pi or base 2 or base 10, which you can always do, is that the slope of the function at the origin is 1. That's where the word natural comes from. So in mathematics, we write it as ln of x. In Julia, it's just log. You don't have to say log e. If you want log base 2, you say log 2 of x in Julia. If you want log base 10, you say log 10 of x. And if you want the natural log, you just say log. Okay, you just say log. And then in engineering, we only use 2e and 10, basically. Unless you're in CS, in which you'll use hex sometimes and stuff like that, but usually base 2, and that's it. Okay, any questions on basic roots, powers, how they're defined, logs, exponentials? Really, these are the 3 things you want to know about logs. Okay. So, log of a product, as long as all of the terms are positive, is the log of the sums. Log of a negative number does not make sense because you take any number bigger than 0 and you raise it to a power, you get a number that's bigger than 0. So log is, there's no inverses because negative numbers are not in the range of exponentials. Okay, so here's the key thing. We're bringing it back now to discussing limits at infinity. So we did ratios, really complicated rational functions with numerator and denominator that can be arbitrarily large order, and we can determine the limits by inspection. It's a beautiful thing when you can just look at it and write down the answer. Everybody agrees with that, I think. That property is still true when you have exponentials interacting with polynomials and rational functions. And the key thing is that a to the x, when a is greater than 1, grows faster than any monomial. And monomials are just things that look like x to the m, where m is a counting number. When a is greater than 0 and less than 1, then as x gets large, it decreases faster than any monomial as well. So the proof of this is given in chapter 1 if you're curious. It's not very hard, but you should only go through it if you're curious. And what I mean by exponentials grow faster than any monomial is you put a to the x where a is bigger than 1, 1.00000001, and you let m be a billion. Now you take the limit as x goes to infinity, you still get infinity. Okay? Exponentials grow faster than any monomial. So if you have such an exponential in the numerator, it dominates no matter how big the term in the denominator is. Reciprocally, or vice versa, or the same, I don't care how big the power in the numerator is, if you have a to the x and a is bigger than 1, as x gets large, this goes to 0. Okay? Exponentials for the base bigger than 1, so e in particular is bigger than 1, dominate. Okay, so I'm giving you 3 functions here. I'm going to give you a chance to write those down. And I don't know, why don't you work on them with a buddy real quick just to check your answers? Okay, so I tried to put some large monomial terms in there. Then I put a less than 1, a bigger than 1, a bigger than 1 here. And I will give a hint that 0.5 is 1 over 2, and 1 over 2 to the x is 1 over 2 to the x, right? So maybe that'll help you out, just in case. But, okay. Okay, so I'm going to ask for our online folks to help us out this time. I've been picking on everybody who shows up, so whatever it takes to get people to come to class, Max, if people just want to sit online, we're going to beat them up. How about that? Okay, so Wyatt, Jason, ooh, okay, Justin, you still there? No, I guess he, illness was taking him too far. Can we answer any of them? Sure. A would be 0. Okay, so we have a proffered answer from online that the answer to the first one is 0. Anybody disagree with that? That's how math works, right? Majority rules? No. Yeah, the answer is 0. Whoops. Come on. 0, and it's because x to the 37 over 2 to the x. So the exponential dominates. It grows faster than the monomial, crushes it, and so we get 0. That's the thought process. I'm trying to give you guys the reflexes for how to set these things up. Ooh, we got some more answers. Okay, for B, we have the answer being proffered as infinity. Ooh, that's a daring answer. So those in class, agree or disagree? So thumbs up, thumbs down. Thumbs up, thumbs down. I see some thumbs up, thumbs up, thumbs up. Everybody went, wow. As soon as you saw a few thumbs up, everybody went thumbs up, okay? So let's just try that with jumping out of an airplane, Max, and see how many of them follow us. And the answer is correct. And it's because this is bigger than 1, so the exponential dominates, and I don't care how big the denominator monomial is, it can't win. And then for C, we also have from online that the answer is infinity. And here the answer is, yep, e to the x is blowing up, and x times it is just helping. Now, if that had been minus x, we'd have gotten minus infinity, okay? So, very good. Okay, you guys did very well. So we got infinity and infinity. Thank you. Okay, well, I got a request to make a problem D, and Luke, you have to solve it. Are you ready? Okay, so f d of x is equal to e to the 3x plus e to the minus 4x plus x to the 100 times e to the x divided by x to the 201 plus 3 times x to the 400, and then 5 times x to 10 to power 100, okay? So what do you think? Is that a dirty enough problem for Luke? Okay, nobody thought I would actually do that. Okay, well, let's just not be totally mean to Luke and look at, well, we've got monomial, and even though this is 10x to a Google, which is 10 to power 100, or is it 10 to power 1,000? I forget, okay? It's a big number. Those are all monomials. This is positive, this is positive, so we have two things getting very large, and this is getting very small. And so the answer is, it also goes to infinity as x goes to infinity. And you would have done the same brilliant analysis, yeah? So, absolutely, okay. Let's do one little piece, and then it'll make our life easier on Wednesday. So, we know how to calculate limits. Let's do some algebra of limits. And Max, since I was kind of trying to go long on Wednesday, let's make sure I go a little tiny bit short so it all averages out, right? Yeah, you'll help me do this. Okay, so let's do some intuition. If I take a real number, I'm going to use Greek letters. And I added infinity to it, what should I get? Infinity. Yeah. So limit x goes to infinity. When I write it like this, that's formal, because we've done limits of rational functions, and there's a very simple rational function. The denominator is 1, okay? So we don't have to fake it, but yeah, that's the intuition. Similarly, alpha is still a real number, and I subtract infinity, I get minus infinity. And it's the same thing. Limit x goes to infinity, alpha minus x, because x is getting arbitrarily large in the negative direction. We know how to do that. Now I ask you, how should I define infinity plus infinity? Whoa. Infinity. How many think it should be infinity? Oh, wow. Yeah. And it's because no matter what quantity, this is, this could have been limit x goes to infinity of x cubed plus 3x. Yeah, so if I break that up, the limit is x goes to infinity of x cubed, that's plus infinity, and if I take x to infinity of 3x, that's infinity. The whole thing is infinity. That's okay. Very good. You guys are right with me. However, infinity minus infinity is undefined. Okay? It is called an indeterminate form. That's a big word. So why can it not be determined? That's what indeterminate means. Cannot be determined. It's a form that cannot be determined. And we'll sketch this out and then stop. And it's because of this. If I do limit x goes to infinity of x minus x squared, what do I get? Which one dominates, x or x squared? X squared. And it's got a what sign in front of it? Negative. So this equals negative infinity. Whoops, negative. Now, if I were to break it up, I'd have limit as x goes to infinity is infinity, and limit of x goes to infinity of minus x squared is minus infinity. So minus infinity, is it always equal to minus infinity? I don't know. Let's see. What is that? Well, I'll do my trick of putting things over a common denominator. X plus 1, then I get x squared plus x minus x squared. These guys cancel. And so what's the limit of x over x plus 1? 1. Okay? And then the limit, the final one, x goes to infinity of x squared minus x. Well, the x squared dominates, and I'll put it as plus infinity just to emphasize, okay? But if I were to be so bold as to break it up into first looking at the limit of the first term and subtracting the limit of the second term, I'd have infinity minus infinity. So all these cases are infinity minus infinity, and depending upon the relative growth rates of the two terms, you get totally different answers. That's why it's called indeterminate. We stop there. Thank you for your attention today. I hope we'll get more of you online coming into class so we have a warm and positive environment for everybody. And that's it. We have homework due. Well, you get a bonus if you turn in your Julia homework by Friday. I forget whether it's midnight or 9 p.m., but it's stated someplace, hidden away on Canvas. I don't know. And then but it's accepted without penalty until Sunday at midnight, 11:59 p.m., just to be clear. And then same for the written homework. So I think you'll enjoy each one. They're quick, fun, and you'll get to play with limits and areas.